Alright gang, had a technical glitch there at the end of the last video, so gonna bring some stuff back. Um, ah, and let's go get our data. Okay, so we've run the ANOVA, and I'm just going to get this back up. So we want our score across our prof, and we can do summary of our model, and we can see our different components that we use to calculate the F statistic, and we can see our p-value. So the previous video I did that, kind of ran through it, again, the calculations by hand, but this one I want to focus on some other things. So first of all, what about the assumptions? What would we want to do there? Well, first of all, to address the independence assumption, I would want to be involved in the collection of the data. So we'll go on and talk about the normality and assumption of equal variances. So guys, hashtag just lets me communicate to you without R thinking it's a command, and won't give me an error. So do we have equal variances? Well, what I would do here is I would use what's called Levenes test of equal variances. So getting back over to the split screen, which I kind of prefer, Levenes test of equal variances in this problem would assume that the variances are equal across Professor A and Professor B and Professor C against an alternative Somebody said it seems like it's almost an ANOVA for variances, and that's, I mean, that's fair enough. But guys, to implement the Levenes test, we have to install a package. Now, if you've already installed the package, all you have to do is access the library. But I don't think we've done anything yet with Levenes test. Maybe we have. It's hard for me to remember because I use videos from previous classes. Well, yeah, here we go. To install a package, what I need you to install here is car. Now, anytime we install a package, the name of the package has to be put in quotations, whereas when we access the libraries, we just type library without the quotations. So, guys, I'm going to install this. I want to scroll down and use US A, California 2, because those are the UCLA folks. And it'll go through its thing and install the package. Now the car package is kind of large, so it may take a while. All right. Once it gets to your prompt, what you have to do is you have to access the library for car. Now notice in library you don't put the name of the package in quotations. It's just library car. Now there's a really cool test. It's called Levenes test. And what we do here is we put our Y, which is score, across our group, which is professor, and we want our data equal data. Now our Levenes test gives us a p-value. It gives us it also follows the F distribution, And we can see here that the F distribution it's using has degrees of freedom 2, 21. And actually, guys, we need to change where the center equals the mean. Okay, so it decreased the p-value, but still we don't have statistical significance. So, guys, our p-value for Levenes test is 0.39, which is greater than our threshold of 0.05. So we can assume equal variances, even though the variance for Professor B appeared significantly higher than the others, for Professor A and Professor C. Okay, so I'm convinced we can assume that we have equal variances from the populations we're drawing from. Now, again, you have to understand we're generalizing here. We're using the sample variances and Levenes test of homogeneity of variance to generalize. So probably because of our small sample, and we probably have inadequate power to really to conduct Levenes test appropriately, we don't have enough power to detect a difference if the difference is indeed there. So, but you know what, guys, you report it and go on with your life and hopefully become famous from your publications. Who knows? Next thing I'd like to look at is normality. I'm going to keep it. I'm going to show you something called Shapiro test of normality, but I'm not going to do it in this video because our sample size is too small, and I think we would get an error. But something I would do, I would want to look descriptively at a box plot, and I would like to look at the score over the professor. And what I would do here is I would examine the IQRs, which is just the box part of the box plot, and see if there's a significant difference, just eyeballing again, to the lengths from Q1 to Q3. And clearly the IQR for Professor B is larger than for Professor A and C, but I don't see any major problems there. Well, let's go for it. But again, I'll teach you a Shapiro test of normality probably in the next video. Okay. Next thing I want to do is let's think more about the test that we just conducted. Okay. We tested the means, the quality of the means for Professor A, B, and C. And of course, this is again back to the ANOVA, not to be confused with Levenes test of equal variances. Against at least one pair of means is different. Well, our p-value was 0.0084, which was definitely less than our threshold of 0.05. In fact, we have a p-value that is statistically significant. This would be reported as p-value less than 0.001. I think this would be a good time to talk about reporting p-values. So reporting p-values. Essentially, in reporting p-values, we have four ways of reporting, four groups, if you will. If our p-value is greater than or equal to 0.05, report it. If our p-value is less than 0.05, but it's greater than 0.01, you would report as p less than 0.05. If our p-value is less than 0.01, but greater than 0.001, then you're going to report p less than 0.01. P-value less than 0.001, report it. So, for example, if you had a p-value of 0.038, how would it be reported? Well, it's less than 0.05, greater than 0.01, so you would report that it is statistically significant at the 0.05 level. If you have a p-value like what we have, this is less than 0.01, but not less than 0.001. So this is statistically significant at the 0.01 level. P-value of 0.52, report it. A p-value of 0.000008, and then reported less than 0.001. So find out the people who have stuck with me through this video when I see how you report your p-values. All right, gang. So what we've done now is we have concluded that our ANOVA is statistically significant. So based on the results of this study, we cannot conclude that the means are equal, but we can conclude that at least one pair of the means is different. Now, how do we determine that? Well, we use what's called a Posthoc analysis. And the one that I want you to focus on, at least for now, is called the Tukey HSD. It's called Tukey Highly Significant Difference. And it's really, really easy to create one of these in R. So all we have to do is just type Tukey HSD of our result for our ANOVA. And what we get is we get the upper and lower bounds along with the p-values for the pairwise comparisons. So guys, what we've done here is the very first one they've done compares B to A. So essentially what they are doing is they are conducting a multiple t-test, but they're doing it in a way where Tukey has created it to control for the inflating of the alpha level, the family-wise type 1 error rate. So what he has done here is he creates a p-value, and it's called a p-adjusted. The p-value here is 0.006, and what we'll do, we'll run a t-test here in just a minute, just between A and B, and I'll show you how a standard p-value for comparing A and B is going to be different than the p-adjusted. So I'll show you that. Now the confidence level is, I'm sorry, the 95% confidence interval for the difference is negative 12.31 to negative 1.97. This tells us there is a 0.95 probability that the mean difference which in this case is mu sub A minus mu sub b. You know, I don't think that's right. I think, yeah, it's not. It's b minus a, so this should be mu sub b minus mu sub a is contained in the interval. Now, guys, anytime we have a p-value less than alpha, our interval will not contain 0. Because if this contains 0, then we must conclude that our mean difference is 0, telling us that the difference in the means is not statistically significant. So let me show you how we can go ahead and look at this, and I will show you how the p-value differs from a p-adjusted to just a standard p-value if we did just a simple, straightforward t-test. Now, if we look at the other, we compared C to A and C to B, so there are 3 comparisons here. Notice that the 95% confidence interval from negative 8.68 to 2.04 contains 0, so I know my p-adjusted is going to be greater than 0.05. And comparing C to B, Professor C and Professor B, I get negative 1.68 to 9.33, contains 0, so I know my p-adjusted will be higher than 0.05. So the reason that we, back on the previous page, the reason that we rejected the null, reason we got a statistically significant ANOVA was all about the comparison between Professor A and Professor B. And it appears to me that, and we can get this back from just our standard, or just basic descriptives. We can see that the difference between Professor A and Professor B is statistically significant because the students from Professor A's class are scoring statistically higher than, on average, than the students in Professor B's class. All right? So, got something going on. Professor A is doing something really, really, really good, or Professor B is doing something really, really, really bad, or a combination of both, or we committed an error. There's no difference at all in the means. We just happened to get kind of a wacky sample that led to an error. But it doesn't matter. Statistically speaking, we have statistical significance, so we could report a higher mean for Professor A than for Professor B. Now, if I wanted to just run a simple t-test, what I would have to do is I would have to create, and I want to bring up my data here, I would have to create a new data set just for my first 17 subjects. So the way that I could do that, and again, this is important on why you set your data set up, the way I talked about back when I was illustrating this in the Excel spreadsheet. What you could do is I could come in and create a new data set, and I'm just going to call it new data. And I could come in with the data function. Now, whatever I initially name my data set, this is what I have to type there. And then I come in with braces. And what happens here is I have a space there. It's going to be separated by a comma. What I put here defines the rows that I want to select. And what I put here defines the columns that I want to select. So what I want is I want to select the subjects, the participants in this study that have ID from 1 to 17. So I'm going to select all of those with ID less than 18. I'm going to leave this blank, and I have to put a space there. I can't let this come all the way over to to the, let me show you what happens if you do that. Okay, you can do that. I thought you had to put a space there, but you don't. So now my new data, notice that all I have are the first 17 subjects. Now, what if I do mean score? Well, that's 32.54. Now, wait a minute. That's the same thing I got when I used my entire data set. The reason being is, even though I've created this new data set, it is still making the calculations based on the data set that we call data. So to change that, what I have to do is I have to attach new data to focus on the new data set that, to access the new data set that focused on the IDs 1 through 17. Now when I do mean score, you're going to see that we get something different because we have different participants. So this allows me to come in and do a t-test of score over prof. And I want to use data equal new data. Now, notice that my p-value when I run a standard t-test was 0.009, whereas the adjusted up here was 0.006. So controlling for the fact that we're inflating this family-wise type 1 error rate, we see that we get a different p-value for the Posthoc comparison that Tukey developed that again compares for that inflation of the family-wise type 1 error rate, and he even mentions that right there, 95% family-wise confidence level. Than we would have if we had just straightforwardly conducted a t-test. All right. You can even see that the confidence intervals 28.75 to well, this is what we need here. So 2.17. You can see that the upper and lower bounds of your confidence interval are also changed, and the reason is because the standard error is different. All right. Well, gang, I think I'm done. I think I've done enough damage in this video, so let's get out of here.